Have you ever wondered what happens when something gets sucked into a black hole? This question marks our journey into the mysterious universe, a realm where the ordinary rules of physics become obsolete, and the extraordinary takes charge. Our first stop is the enigmatic black hole. Imagine a region of space-time so potent with gravitational pull that nothing, not even the fastest entity in the universe, light, can escape its clutches. This is what we call a black hole. An abyss in the fabric of space-time. A black hole is an entity which, once crossed, marks a point of no return. The concept of black holes is not born out of fantasy. Instead, it is deeply rooted in the theory of general relativity. This theory, proposed by one of the greatest minds mankind has ever known, Albert Einstein, predicts that a compact mass can distort space-time, giving birth to a black hole. It's like pressing a heavy ball onto a stretched rubber sheet. The ball creates a depression, a hole, and anything that comes too close falls into it. But what makes black holes truly fascinating is their event horizon, the boundary of the black hole from which nothing can escape. It's like the edge of a waterfall. Once you go over, there's no swimming back up the stream. Black holes are truly the ultimate masters of hide and seek. They reflect no light and even emit a unique radiation called Hawking radiation, named after the brilliant physicist Stephen Hawking. But here's a question that might make you scratch your head. If black holes are entities from which nothing, not even light, can escape, then how did we come to know about their existence? How did we uncover these cosmic hide-and-seek champions? Well, it's a tale as fascinating as the black holes themselves. So if light can't escape from a black hole, how did we come to know about them? Stay tuned as we delve deeper into this cosmic mystery in the next scene. Our journey begins in the 18th century with John Michell and his revolutionary proposal. In the year of 1784, a man named John Michell proposed an idea so radical, it was met with skepticism. His idea was a concept that shook the very foundation of our understanding of the universe. Michell proposed the existence of what we now know as black holes. He envisioned regions of space-time where gravity was so immense that nothing, not even light, could escape its grasp. However, the idea was so far-fetched, so against the grain of the known laws of physics, that it was largely dismissed by his contemporaries. The concept of something so dense, so powerful that it could trap light was unimaginable, seeming more like a work of science fiction than a plausible reality. Yet Michell's idea was not entirely forgotten. It merely lay dormant, waiting for the right minds to pick it up and breathe life into it. Fast forward to the year 1915. Enter Albert Einstein, a man whose name has become synonymous with genius. Einstein's revolutionary theory of general relativity provided the theoretical foundation that Michell's idea sorely lacked. According to Einstein, a sufficiently compact mass could indeed deform space-time, creating a black hole. Einstein's theory was a breakthrough, a leap forward in our understanding of the universe. It gave credence to Michell's idea, transforming it from a fanciful notion to a serious scientific proposition. Yet it was only a theory, a mathematical model. It provided the theoretical possibility of black holes, but it did not prove their existence. But it took more than just theory to convince the scientific community about the existence of black holes. The world had to wait for more concrete evidence, for observations that would irrefutably prove the existence of these fascinating cosmic objects. That evidence, however, was yet to come, and it would bring with it a new era of understanding about the mysterious universe we inhabit. Science needed evidence, and it came from an unexpected quarter. In the year of 1967, a significant discovery was made in the field of astrophysics: neutron stars. These compact celestial bodies, the remnants of supernovae, sparked a renewed interest in the theory of black holes. The neutron stars, with their immense gravitational pull and compactness, served as a tangible proof of the existence of other, even more extreme astrophysical objects: the black holes. Around this time, a brilliant astrophysicist named Subrahmanyan Chandrasekhar was delving into the peculiarities of electron-degenerate matter. His computations led to the identification of a limiting mass for stable solutions of such matter. This limit, now known as the Chandrasekhar limit, is roughly 1.5 times the mass of our Sun. Any stellar object exceeding this limit cannot resist the gravitational pull by the virtue of electron degeneracy pressure alone, and is destined to collapse into a denser state such as a neutron star or a black hole. Following Chandrasekhar's work, Robert Oppenheimer, the father of the atomic bomb, turned his attention to the stars. He predicted that neutron stars above a certain limit would inevitably collapse under their own gravity to form black holes. This was the first instance where a concrete prediction was made about the formation of black holes from celestial bodies. These scientific breakthroughs were monumental. They provided the much-needed evidence to substantiate the existence of black holes. The black hole was no longer a mere theoretical concept hypothesized by John Michell in the 18th century and later refined by Albert Einstein's general relativity. It had become a tangible entity within the realm of astrophysics. And thus, the black hole moved from the realm of theoretical physics to tangible astrophysics. Black holes are not all the same, they come in different sizes and have different origins. Similar to the variety of life on Earth, the universe too boasts a diverse cast of black holes. Let's begin by talking about stellar mass black holes. These cosmic entities are born from the dramatic demise of massive stars. When such a star exhausts its nuclear fuel, it can no longer resist the force of its own gravity. It collapses under its own weight, and in the process, the core of the star gets squeezed into an incredibly dense point. This point, known as a singularity, is the heart of a black hole. The resulting black hole is typically a few times the mass of our sun, but incredibly compact. Imagine cramming 4 suns into a sphere just 6 miles across, and you get a sense of how dense these objects are. But the universe doesn't stop there. It scales up the black hole concept to a level that's almost impossible to comprehend. Enter supermassive black holes. These are the leviathans of the black hole world, with masses millions or even billions of times that of our sun. How exactly these behemoths form is still a topic of active research, but one leading theory suggests that they grow by absorbing other stars and merging with other black holes. This process of growth and merger can lead to the formation of incredibly massive black holes at the centers of galaxies, including our own Milky Way. So we have stellar mass black holes and supermassive black holes, each fascinating in their own right. But here's the intriguing part: they're invisible to the naked eye. These cosmic entities don't reflect light or emit anything we can see. But how do we detect something that doesn't reflect light or emit anything we can see? Stay tuned as we delve into this question in the next scene. Detecting a black hole is like trying to see the wind. We can't see it directly, but we can observe its effects. This statement is a fitting metaphor for the elusive nature of black holes. These celestial phenomena, despite their invisibility, make their presence known in rather dramatic ways. Black holes are incredibly massive, and their gravity is so strong that it warps the fabric of space-time itself. This warping is not just a theoretical concept, but it has observable consequences. When other celestial bodies, such as stars or gas clouds, come close to a black hole, they don't just continue on their merry way. Instead, they start to move in unusual ways, their paths distorted by the black hole's immense gravitational pull. These distortions can be detected and measured, giving us indirect evidence of a black hole's presence. One of the key features of a black hole is its event horizon. This is the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. While the event horizon itself is impossible to see, we can infer its presence when we observe matter spiraling towards a point from which no light emerges. This spiraling matter, heated to incredibly high temperatures by the black hole's gravity, emits X-rays that can be detected by our instruments. Another fascinating aspect is the concept of Hawking radiation. This theoretical prediction by physicist Stephen Hawking suggests that black holes are not entirely black, but emit tiny amounts of thermal radiation due to quantum effects near the event horizon. While this radiation is incredibly weak and has not yet been detected, its existence would offer further proof of black holes and their strange properties. Black holes are a testament to the power of scientific inquiry. Despite being invisible, their effects are so significant that we cannot ignore their presence. By studying their interactions with other matter and electromagnetic radiation, we can continue to learn more about these mysterious entities and their role in the universe. So black holes, once just a theoretical concept, are now a fascinating and mysterious part of our universe. Our journey through the history and science of black holes has been quite a ride. We've navigated the inception of these cosmic phenomena, journeyed through the development of general relativity, and marveled at the discovery of neutron stars. We've witnessed how different types of black holes come into existence and delved into the ingenious methods scientists use to detect the undetectable. As we conclude, let's not forget that in the vast expanse of the universe, black holes are just one of the many fascinating phenomena waiting to be explored.